Okay, this is the Topology 2 course for the Math and Master program, and the lecture is number 7 in the booklet, and it's about singular homology. Now, singular homology is, in many respects, the best homology theory that there is. It has only one serious drawback, is that it gives no intuition whatsoever, no geometric intuition of what homology is. Another defect that it has is that it views directly is not any good for computing homology groups by using the definition. By using the definition, the only homology group that you can compute is the homology group of a point. So let's begin with some definitions. Main definitions. So the first definition is a singular simplex. And the singular simplex is simply a continuous map of an n-dimensional simplex which we'll usually denote as follows. To the given topological space X. So X is a topological space. And the map, of course, is continuous. Now, a face of a singular simplex sigma n, denoted sigma ni, is by definition the given singular simplex restricted to its subsimplex dn I, where d and I is by definition the simplex with vertices 0 and so on. Then the ith vertex is emitted, and then n. So this is the definition of a face. And now we can define the chain group. Chain group Monica, do you see what I'm writing?
Yeah, I mean, if you move a bit, yes.
Okay. A chain group, which is denoted as chain groups usually are, Cn of x, and by definition, the chain group is the set of chains, each chain being a formal linear combination over alpha, or alpha with any index, of z alpha. The z alpha are integers, sigma and alpha. An important requirement is that the sum is finite. We require the sum to be finite. And the z alpha, as I said, are integers. So this is the notion of chain group. And the next definition, of course, will be that of a boundary operator. The boundary operator, Dn, is a homomorphism from the chain group Cn to the chain group Cn minus 1 of x. And it is given by the following formula, which incidentally should look quite familiar. So the boundary operator on a simplex, or more precisely, on a chain consisting of a single simplex with coefficient plus 1, this is by definition what you think it's going to be. It's the same definition that we considered in our study of simplicial homology. Okay, let me repeat all of these things. We first define a singular simplex simply as a continuous map of a geometric simplex to the given topological space. A face of a simplex is the restriction of the given simplex on a face of the geometric simplex here. A chain group is the set of all finite linear combinations of simplices with integer coefficients. And we define the boundary operator exactly as we did when we were defining the boundary operator for simplicial homology, namely by defining it on a simplex by this formula, and then extending to the whole chain group by linearity. Now, the next thing that I want to mention is the Poincaré lemma. Oh, let me get another. Poincaré lemma, which says what you think it's going to say, namely, if you do dn minus 1, dn plus 1, and then follow that with dn, you get 0. And this is the same as saying that the kernel of dn contains the image of the n plus 1. The proof of the Poincaré lemma is exactly the same as the proof of the corresponding lemma for simplicial homology. And I will write very briefly the simplex sigma ij, the one where the i's and the j's vertex have been omitted, appears twice or with opposite signs. So much for that. Now my next step is to state what is usually called the chain morphism lemma which says the following: if you have a continuous map F of a topological space X to a topological space Y, then a morphism of the corresponding chain groups arises. Let me write it out. So we have Cn X. We have the boundary operator Dn working here, which takes this chain group to Cn minus 1 of X. And then this continues. Here we have Fn, which takes this chain group to this corresponding chain group in Y. Here we have delta n. Well, I'll write X here and Y here so that we don't confuse these two different boundary operators. Here we have C n minus 1 of Y and F n minus 1, and so on in both directions. And the chain morphism lemma says that the square commutes. This lemma follows directly from the definitions. You just have to apply the definitions to check that. Now, the Poincaré lemma and this lemma together have the following corollary. These chain groups taken together form a functor from the category of chain complexes to the category of graded abelian groups. And also, this fact implies we have actually constructed a functor called the singular homology sumco. Is a functor from the category of topological spaces to, oh, I'm sorry. Yeah. No, this is everything okay. Graded abelian groups. Okay, so that's the first part of the lecture. Now for the really good news, which would have been a sensation if singular homology was defined a century ago. Namely, it follows immediately from definitions that singular homology is a topological invariant. Why would that have been a sensation? Well, because the proof of the fact that simplicial homology is a topological invariant took many years to be achieved, and it was always extremely complicated. Okay, so we have constructed singular homology theory. And let's continue with some remarks on some properties of singular homology. Namely, I will begin with an important property, that of being an invariant of homotopy. So I don't need any of this anymore. So our next step in this lecture is to prove the homotopy invariance of singular homology. Now this proof will also be quite difficult, just as difficult as the proof of homotopy invariance of singular homology, simplicial homology. Why is that? Well, for the following reason. Now, in the definition of homotopy, we take the direct product of a simplex by the unit interval. And this Cartesian product is not a simplex. So in order to continue working with homotopy, we have to devise a special way of working with these objects. More precisely, we will need to triangulate in a canonical way the product of a simplex by a segment. So what I want to do at this point is to increase this diagram a little bit. Cn plus 1 of x. Here we have d n plus 1 of x. Here we have f n plus 1 and c n plus 1 of y here. And this, of course, is d y n plus 1. And we'll have arrows going this way as well. So our aim is to prove homology invariance. Let me write this out. What does homology invariance say? It says that if f and g are maps from x to y, continuous maps, of course, and they are homotopic, then we have the fact that the induced homomorphisms coincide. Okay, to do that, we are going to use, as you have guessed, the chain homotopy level, the lemma, which, let me remind you, it says that there exists a sequence of homomorphisms in this diagram, such that the corresponding triangles commute. So the difficult part of the proof is the construction, the actual construction of these homomorphisms. Together they constitute what is called a chain morphism. And the chain morphism lemma says that if you have these guys, dn, dn minus 1, and so on, in this diagram, then you can conclude that the induced homomorphism homologies coincide. This, of course, you should remember, means that also the corresponding homology groups are isomorphic. From this fact, by a very simple argument that this follows, that the homology groups of a fixed topological space of two topological spaces, which are homotopy equivalent, are isomorphic. Okay, so now our next aim is to define these guys dn. To do that, we will consider the following situation. Let me draw another picture here. We have our space X up here. We have our space Y down here. We have a map F. And here we have a singular simplex. Now, this singular simplex is actually a map of a geometric simplex to here. We are going to construct a homology of this map. Well, we're given, in fact, a homology of this map. And so we have something like that here. And this is taken down to Y or in some way. And what we want to obtain is a homology between these two singular chains. So as usual, we're going to define dn on one simplex, or more precisely, on a chain consisting of one simplex with a coefficient +1. And this is how we're going to go about it. The first thing we will look at is we'll do this by induction we'll do this successively for a different dimension 1 and dimension 2. So in dimension 1, we have a simplex multiplied by 0, 1. So this is my simplex. It is multiplied by 0, 1. And we need to triangulate this. So this is 0, 1 here. We need to triangulate this object in a certain specific way, and we're going to do it canonically as follows. We denote 0, 0 and 1, 0 the vertices of the given one-dimensional simplex. And then we consider two simplices. One simplex is, and these vertices will be denoted 0, 1 and 1, 1. And so the canonical triangulation of this Cartesian product will consist of two simplices, namely 0, 0, 1, 0, and 0, 1. That's one simplex, and the other simplex will be 1, 0, 1, 1, and 0, 1. Now let's consider the case in dimension 3. I will not do the general case in dimension n. Once you've understood the situation for dimension 3, it will be easy to generalize to any n. So here we have a two-dimensional simplex, there it is, multiplied by 0, 1, by the segment 0, 1. So it's a kind of prism with triangular base. We divide this prism into three-dimensional simplexes, as shown on this figure. So this is one in the middle, it's in red. This one is the one that has this face. And finally, in blue, you have the simplex. It goes like that. Let me write out the names of the vertices and the names of the simplices. So this vertex will be 0, 0. This will be 1, 0. And this will be 2, 0. And upstairs, we have 0, 1. Here, 1, 1. And here, 2, 1. And the simplices are this. First, we take 0, 0, 1, 0, 2, 0, and then 0, 1. This is the black simplex. Then the red simplex will read we start here, so it's 1, 0, and then 2, 0, and then these two guys upstairs, they are 0, 1, and 1, 1. And now for the blue simplex, we have only one vertex downstairs, which is 2, 0. Which is 2, 0. And then we have these three guys who are 0, 1, 1, 1, and 2, 1. So we have found a triangular, canonical triangle, triangulation of the direct product of a geometric simplex by 0, 1. So we have it here now. And what we have here are actually two singular simplices of dimension 2. So this situation will allow us to define the n. We will do this as follows. It's not at all trivial. So what do I have? I have a commodity called Ft of x to y. Which begins with f and ends with g. We're doing this. Now I will define dn on a simplex on a sigma n, or to be slightly more precise, on a chain consisting of one simplex with non-zero coefficient, with non-zero coefficient being equal to +1. And then I will extend by linearity as always. So to define that, I'm going to construct some additional maps. First, capital gamma is the map of the simplex dn multiplied by 0, 1. So it's this simplex here. To y. So that's the map from here to here. By setting d, a point dt, d is on a simplex, t is on a segment, is by definition, well, I will not write the definition. By definition, simply f t of sigma d. So that's the first definition that I need. I will also need a linear map, which I will call epsilon. N plus 1. Of the simplex d n plus 1. I'll map the simplex linearly to dn cross 0, 1. And I will do this in the following way. If I will take the jth vertex of n plus 1, so the jth vertex I will take to the vertex j0, Now, this J0 refers to these vertices. And J plus 1, I will take to J1. And now I can define dn on the simplex, on the singular sigma n, and I will define it as follows. I will write out the formula. It's the sum over I from 0 to n of minus 1 to the jth power gamma delta n plus 1. Oops, it's not. Sorry. This was not epsilon, it was delta. Delta n plus 1 applied is this, which is an element, as you can see, of C n plus 1 of x. So, and then I extend to linear by linearity. So let me repeat this whole thing. I need two auxiliary maps. One is gamma, which is given by the homotopy that we have between x and y. The homotopy between f and g that we have. That's one. And another rather clever linear map of a n plus 1 simplex to this singular, this simplicial complex. This is a simplicial complex in the canonical triangulation that we have defined here. So to define a linear map, you just have to say where the vertices go. Well, they go according to this rule. And so, taken all together, we have the following definition. And you can check that the definition works. And that indeed, we do have commuting triangles here and here. Now we apply the chain homotopy lemma and conclude that we have homotopy invariance. Okay, so that's the second part of today's lecture. The most difficult part, the rest will be on easygoing by comparison. Now I want to go on to the properties of singular homology. Which are often called Spinrad-Eilenberg axioms rather than properties. So let's entitle this section 3. Oh dear. Properties of singular homology, which are also known as the Steenrod Eilenberg both Steenrod and Eilenberg are American mathematicians who worked in Princeton in the golden era of Princeton mathematics. And Steenrod stayed at home in Princeton, whereas Eilenberg moved to France and mostly worked out from France, where he in particular became one of the members of Bourbaki. Here are the main properties of singular homology. First, I will explain what the homology functor is. So the homology functor, what does it do? For any n greater than or equal to 0, we have an assignment to any topological space. We assign an abelian group, actually a Z-module, and to any pair of spaces. This functor assigns an abelian group denoted Xn A. It does many other things. To any pair X A, it assigns a homomorphism D star, which I'm sure you sadly remember. It's not too simple to define, but we have defined it several times. XA to H n minus 1 of A. And then to any map, continuous map of a space X to Y, to that, it assigns a homomorphism F star from H n of X to H n of Y. And finally, to any map of pairs oh, sorry, pairs. So any map of pairs, it assigns, well, I won't write what it assigns. You can write that out yourselves. So I claim that this is a functor. So this is a description of a functor. This is what it does. It does all these things. And now I claim that is a functor. So I'll write that in the following way. I'll write this as functoriality. So we have functoriality. Then we have the first property, very simple property, which says that which is called dimension, or sometimes some people call it normalization. It says that the nth homology group, the zero homology group of a point, is Z, and the nth homology group for n greater than or equal to 1 of a point is 0. That's dimension. And the next one is called commutativity. And that says the following. If we look at the diagram, H n of xa, which is taken by d star to H n minus 1 of A. Then we have here Hn of YB, with of course F star. And this here. Here we have D star. Well, I'll add the letter Y here and the letter X here so that we don't confuse these two objects. And here we have H n minus 1 of B. Here we have also a star in the other dimension, which I have not written out. And so this diagram commutes. So that these are the first two properties of the functor of simplicial homology. And we go on to the next one. So about the proofs. Well, this is obvious. This follows from definitions directly. There's no tricks, nothing clever about this. It's just checking the definitions. Now the next is homotopy invariance. I will not write out what this means. It consists of two facts. one concerning morphism, the other concerning objects. And then we have property called exactness. Which says that the sequence Hn of A, Hn of A mapped by I star to Hn of Xa, and this in its turn mapped by J star to Hn of X. And here we have D star. And that takes this to I'm sorry, I got this wrong. Of course, this is Hn of X. This is the inclusion, the induced map from the inclusion of A into X. And from this, we have J star, which says that we look at a chain in X as a chain, as a relative chain. So this is Xa here. And D star takes us to Hn minus 1. This was N, and here we have N minus 1 by, and things continue in the same way. So that's exactness. And there is one more property that I want to state, which is the last of the Steenrod-Eilenberg axioms. And it says the following. It is called excision. We have mentioned it before in the setting of simplicial homology, and it says that if you have a space X which contains a subspace A, it's just simply topological spaces, which in its turn contains an the interior of A, the interior of A, and that contains U. This is this is contained in the closure of an open set, and a U is this open set. In this situation, you have the following isomorphism: H and X A is isomorphic to H n of X minus U A minus U. So let me briefly repeat what I have said. We are now listing the properties of a singular homology. The singular homology functor is a big machine that does all these assignments, which were explained today, and satisfies the following properties. It is a functor. It behaves reasonably with a point. The operator D star is part of a commutative square here. We have homotopy invariance, which we proved with some serious work before. And we have an exact sequence for pairs. And we have the excision property, which says that if we throw out something which is very much inside of A, it's very much inside of A. From X and from A, and then we get isomorphic homology groups. So that is all for the properties. Well, the next thing that I want to state is the Meyer-Vietoris sequence, which we have already seen in the other homology theories. But here it is slightly more delicate. It will work under a certain assumption, which I will now explain.
Oh, sorry. We will not see the proof of excision theorem, right? Because it's a bit complicated, I remember.
Say that again?
We will not see the proof of excision, right? Because it's a bit complicated, I remember.
What was complicated?
The proof of excision.
Yes. Oh, yes. I forgot to say that. Thank you, Monica. The excision axiom is not easy to prove, and if you want to learn a proof, I'll give you a reference.
Okay.
It is
yeah.
Russell's book.
Okay.
On the Breslov book, on which is called Elements of Homology Theory.
Okay.
Some pages 198.
Okay.
100. So it's 2.5 pages. It's not too difficult, but it's not trivial at all. If I had more time, I would tell you the truth. But
okay, thank you.
Now, so what is the situation with the Meyer-Vietoris sequence? Vietoris, incidentally, is a mathematician who lived to the age of 105 years. So we say, suppose we have a space X containing two subspaces, X1 and X2, such that the union of X1 and X2 is X. We say that these spaces satisfy the excision condition if we have if the morphism Cx1 plus Cx2 of chain groups. Let me explain what all this means. What is an element of this? It is a chain which consists of certain simplices of x1 and certain simplices of x2. It is naturally mapped to the corresponding chain in C, a chain in X. This mapping is essentially the identity. It's just the same chain. So here it's a chain which is the sum of two chains, a chain from here and here. And the sum is actually just a chain in X. The excision condition says that it induces an isomorphism in homology. In that case, okay. So I'll state this as a theorem. We have all this. Then the following sequence H n of x1 intersected with x2, which is naturally mapped to H n of x1 plus H n of x2 then this is mapped to H n of x, and then this is the interesting part. We have a D star here, which takes this to H n minus 1 of the intersection. And so on. So, sequence. Then this thing is exact. So let's prove this. Let us write the following short, exact sequence of chain complexes. And here, instead of this chain C of x, we're going to write the chain C x1 plus C x2 and 0. These morphisms are the natural ones. The fact that this thing is exact is obvious, practically obvious here and here and here and here. So by the chain morphism, short to long, by the short to long lemma implies that this sequence is exact. Okay, so we have one more thing to go in today's lecture, and this is a series of uniqueness theorems, which basically say that all the homology theories that we have studied, and many others, are equivalent in the sense that they give the same homology groups and the same induced homomorphisms. So this is the last section, section 5, it's uniqueness. Theorems. And so we have the following theorems. Theorem 1. In the category of topological spaces, and continuous maps, any functor satisfying the Steenrod-Eilenberg axioms 1 to 5 produces the same groups and homomorphisms as the singular homology functor. So that's the first theorem that I want to mention. I will discuss the proof of these theorems after I have stated all of them. There will be three of them. So that's one theorem. Theorem 2. In the category of simplicial spaces and simplicial maps, or any functor satisfying axioms 1 to 5 produces the same groups and homomorphisms as simplicial homology. So let me repeat these two theorems before I state the third one. Their formulation is similar in the corresponding categories. Singular, any functor satisfying the Steenrod and Eilenberg axioms yields the same homology groups and induced homomorphisms. Here as singular homology, and here as simplicial homology. And the next theorem, which incidentally is not in the booklet, is theorem 3. On the category of CW spaces and cellular maps. You still remember what a cellular map is, by the way? A functor satisfying axioms 1 to 5 produces the same as the cellular homology functor. Now, a corollary of these three theorems is that any two of the three theories that we have constructed, namely singular homology, simplicial homology, and cellular homology, when we consider them on spaces where they're both defined, then they give the same results. So the three theories are the same. They only differ in that the category on which they are defined is different. But if one of them is defined on a subcategory of the other, then the two of them have the same homology groups and induced homomorphisms. Now, about the proofs. This is quite difficult. This is quite difficult, but it is a particular case of a statement, a very general uniqueness theorem proved by Steenrod and Eilenberg. In a book which I have, I hope I wrote down the reference. The book is called Foundations of Algebraic Topology. And this was published in 1952. This has a very general uniqueness theorem for a very wide class of categories. These categories include the category of topological spaces. And so singular homology is indeed unique in this sense. Now, concerning the category of simplicial spaces and simplicial maps, any functor this uniqueness theorems here can be proved mainly by using homotopy invariance and the Mayer-Vittori sequence. The general idea being this: it works in the case of compact simplicial spaces, finite number of simplicity. The idea is this: you take a simplex of the main dimension, then its homology group is 0. Sorry, its homology groups are 0 in all dimensions except 1, 0 when they are equal to z. This follows from the dimension axiom and from the homotopy equivalence. The simplex, of course, is homotopy equivalent to a point. Then we add a second simplex. We compute its homology, which is the same as this one here. Now, we compute the homology of the intersection. Then we use the Mayer-Vittori sequence to compute the homology of their union, and so on. And in this way, you eventually get to we eventually construct the whole space and get the result. Concerning this theorem, it has a very nice proof, which I'm sorry I did not write up in the booklet. And it is, it appears in the Fomenko-Fuchs book. Which is called a homotopic topology. And it's in section 13, theorem 7. So that's the end of the story. We have these three nice uniqueness theorems. For two of them, you can more or less understand their proofs by reading this book, or in this case, by using the Maya-Vietoris sequence. And so, in a certain sense, we have reached a milestone in our development of homology theory. And the next lecture, which will not necessarily be at the same time next week. I will notify everyone. Possibly I will shift it to the afternoon, so that to the late afternoon, so that Daniel will be able to tune in on the lecture directory. But well, you'll be notified in due time. And the next lecture will be already on the applications of the theory. We'll be applying all three theories at once, because we know that they give the same results. And we'll use the appropriate theory depending on the situation to prove these properties as simply as is possible. Well, thank you for the attention. I'm sorry about the beginning of the lecture.
Okay. Thank you.
Now, I don't